universe is filled with awe-inspiring phenomena, but some celestial objects are so bizarre that they stand out even beyond the familiar stars and planets. From giant bubbles in our Milky Way to vast, near-empty voids and objects that seem to defy the very laws of physics, these unusual structures are challenging our understanding and providing new perspectives on the cosmos. Join me on a journey to explore the weirdest objects in the universe. Tonight, as part of our Exploring the Universe series, we will take a close look at the orbits of stars like S2, discuss how they validate general relativity, and explain concepts from redshift to the shadows of black holes, all while confronting the ultimate questions of civilizational survival. It is a long story, so let us begin the journey. But before we start, don't forget to like and share. Imagine a star spinning so fast that it pushes the very limits of what we thought was physically possible. PSRJ 1748-2446 AD is exactly that kind of star. We call it the Whirlwind Star. It is the fastest spinning pulsar ever discovered, rotating at a staggering 716 times per second. To put that in perspective, it spins faster than the blades of a helicopter. Such extreme rotation raises profound questions about the fundamental forces in the universe and makes the Whirlwind Star one of the most extraordinary objects in space. To truly understand this object, we first need to know what a pulsar is. Pulsars are a type of neutron star, the incredibly dense leftover cores of massive stars that have undergone supernova explosions. A neutron star packs more mass than the Sun into a sphere only about 20 kilometers in diameter, roughly the size of a small city. The density is almost unimaginable. A single sugar cube-sized piece of neutron star matter would weigh about 1 billion tons. What makes pulsars unique is that they emit beams of radiation as they rotate, much like a cosmic lighthouse. If one of these beams happens to point toward Earth, we detect it as a periodic radio pulse, which is how they earn their name. The Whirlwind Star is located about 18,000 light-years away in the Tirzan 5 globular cluster, a region densely packed with stars, many of which are among the oldest in the universe. What sets this pulsar apart is its incredible rotational velocity of 716 Hz, far exceeding any other pulsar discovered to date. If Earth rotated at this speed, a day would last less than a millisecond. This extreme spin is not accidental. Over time, a pulsar can be spun up through a process called accretion. When matter from a binary companion star falls toward the pulsar, it transfers angular momentum and energy as it spirals inward, causing the pulsar to rotate faster and faster. The Whirlwind Star reached its breathtaking rate through this exact mechanism. When an object spins this fast, a natural question arises: why doesn't it tear itself apart? The answer lies in the extreme gravitational pull of the neutron star. These objects possess some of the strongest gravitational fields in the universe, providing a massive inward force that offsets the centrifugal force generated by the rotation. However, scientists believe the Whirlwind Star is approaching the breakup limit, the theoretical maximum speed a neutron star can reach before disintegrating. Being so close to this limit provides researchers with vital clues about physics under extreme conditions. The fact that the Whirlwind Star resides in Tirzan 5 is also intriguing. The high concentration of pulsars in this cluster makes it a premier laboratory for study. This abundance is likely due to the extreme stellar density within the cluster, where stars interact more frequently, making the spin-up process much more likely to occur. In other words, the crowded environment of Tirzan 5 provides the perfect conditions for the formation of millisecond pulsars. Of course, the discovery of the Whirlwind Star would have been impossible without advanced technology like radio telescopes, such as the Parkes Observatory in Australia. These instruments capture the faint signals emitted by high-speed pulsars, and by precisely measuring the time of arrival, TOA, of these pulses, astronomers can determine the exact rotation rate. These observations are more than just interesting facts, they allow scientists to test the most fundamental theories of physics, such as Einstein's general relativity, under conditions of intense gravity. The Whirlwind Star is not just a marvel of speed, it is a scientific tool pushing the boundaries of physics, allowing researchers to study the behavior of matter under pressures and gravitational forces that simply cannot be replicated on Earth. Looking ahead, future facilities like the Square Kilometre Array, SKA, are expected to find even faster pulsars, opening the door to the most extreme conditions in the universe and perhaps providing clues to the very nature of matter. While the night sky is dominated by stars, quasars, some of the most energetic and luminous objects in the cosmos, can outshine entire galaxies. 3C273 is the brightest quasar visible from Earth. Discovered in 1963 and located in the constellation Virgo about 2.4 billion light-years away, it stands as a landmark in astronomical history. But what exactly is a quasar? Quasars are high-energy galactic nuclei powered by supermassive black holes. As gas and dust spiral into the black hole, they are heated to extreme temperatures, releasing massive amounts of energy across the entire electromagnetic spectrum from visible light and radio waves to X-rays. A quasar can be hundreds of times brighter than its entire host galaxy. 3C273 itself is about 4 trillion times more luminous than our Sun. Its discovery marked a turning point in our understanding of the universe. In the early 1960s, astronomers detected unusual radio signals from objects that looked like stars but were far too powerful. The breakthrough came when Martin Schmidt and his colleagues studied the spectrum of 3C273 and found a significant redshift, indicating that the object was moving away from Earth at an incredible speed. This redshift placed 3C273 far outside our Milky Way, revealing it to be a distant, active galactic nucleus rather than a local star. Even at a distance of over 2 billion light-years, 3C273 is so bright it can be seen clearly through telescopes. Its core contains a supermassive black hole actively consuming surrounding matter, generating energy that traverses the cosmos. This makes it an essential tool for studying distant galaxies and the early universe, helping scientists map large-scale structures and understand the distribution of galaxies in space. The discovery of its high redshift was a milestone. Redshift occurs when the expansion of the universe stretches light to longer wavelengths as an object moves away from us. For 3C273, This not only proved its vast distance but also established it as one of the most powerful objects known at the time. This shifted our perception of the cosmos, showing that there are countless powerful objects far beyond our own galaxy. Since then, thousands of quasars have been identified, each helping us understand the behavior of supermassive black holes and the formation of galaxies. 3C273 is not just a visual spectacle, it is a window into the early universe. Like a cosmic lighthouse, it helps us navigate the distant reaches of space and time. While the term quasar has inspired countless science fiction stories about extreme phenomena, the reality of 3C273 remains one of the most profound discoveries in our quest to understand the universe. Pulsars are inherently fascinating, but PSRB 1257+12, often referred to as Lich, takes the spectacle to a whole new dimension by hosting its own planetary system. Located in the constellation Virgo, about 2,300 light-years away, this pulsar is orbited by planets, a groundbreaking discovery from the early 1990s that marked the first time planets were ever detected outside our solar system. This raises a profound question: how can planets possibly exist around a dead star? To understand this, we must recall that a pulsar is the collapsed core of a massive star remaining after a supernova explosion. They are incredibly dense, rotating rapidly and emitting lighthouse-like beams of radiation that sweep across the sky. Lich is unique because it hosts at least 3 planets, named Phobiter, Dragr, and Poltergeist. These worlds range in size from slightly smaller than Earth to several times its mass, but the similarities end there. Imagine standing on one of these worlds. Instead of a warm, life-giving sun, you would see a tiny, rapidly flickering point of light constantly bombarding your world with high-energy radiation. The solar flares from this pulsar's intense magnetic field would make our sun's activity look insignificant. For life as we know it, these planets are utterly uninhabitable, stripped of atmospheres and scorched by constant radiation. The true mystery is their origin. Since a supernova usually destroys everything in its vicinity, were these planets survivors of the blast, or did they form afterward from the debris? Scientists propose 2 main theories: either they are second-generation planets that coalesced from the post-explosion dust disk, or they somehow survived the cataclysmic death of their parent star. Regardless of which is true, the Lich system proves that planetary systems can emerge and persist in the most unexpected and violent environments. The 3 planets orbiting Lich, Poltergeist, Phobiter, and Dragr are situated at distances comparable to Mercury's orbit around our Sun. Even though similar in size to Earth, are likely nothing more than barren, irradiated rocks. Their discovery relied on pulsar timing, a technique that measures tiny variations in the pulse arrival times caused by the gravitational tug of orbiting planets. This precision method revolutionized the search for exoplanets, long before we began finding them around Sun-like stars. Lich taught us that planets can exist around almost any type of star, even dead neutron stars. While the surface conditions are far too harsh for life given the constant radiation and lack of atmosphere, some scientists speculate whether life could find a foothold deep underground, shielded by layers of rock. After all, we find extremophiles on Earth in the most inhospitable places. While this sounds like science fiction, Lich's challenges are preconceptions about where life and planets can exist. Much like the Whirlwind Star or the supermassive black hole Sagittarius A*, this system pushes the boundaries of possibility and reminds us that the universe is full of surprises, perhaps with many more zombie planetary systems waiting to be discovered. Pushing the limits of extremity even further, we encounter the Cosmic Cannon, a magnetar located in the constellation Sagittarius, about 50,000 light-years away. A magnetar is a type of neutron star with a magnetic field so powerful it defies imagination, billions of times stronger than energy photons. Magnetars are rare and have short active lifespans of about 10,000 years before their magnetic fields decay. They force us to rethink the upper limits of stellar remnants and the sheer power that can be unleashed by a collapsing star. Finally, we look at S5HVS1, a star that belongs to a completely different category, hypervelocity stars. While most stars in the Milky Way drift at 20 to 30 kilometers per second, S5HVS1 is screaming through space at an incredible 1,200 kilometers per second, about 4.3 million miles per hour. Such stars are not born fast, they are accelerated by violent cosmic events. S5HVS1 likely began its journey as part of a binary system that ventured too close to the supermassive black hole at the center of our galaxy. Through a process called the Hales mechanism, the black hole's immense gravity captured one star and acted as a gravitational slingshot for the other, flinging S5HVS1 away at impossible speeds. It is now on a one-way trip out of the Milky Way, destined to become a rogue star drifting in the vast emptiness between galaxies. Studying these escapees helps us understand the dynamics of black holes and the scale of our galaxy. S5HVS1 is, like a survivor of a near-fatal encounter, a testament to the destructive and transformative forces at the heart of the cosmos. From the zombie planets of Lich to the magnetic fury of the Cosmic Cannon and the lonely flight of the hypervelocity star, these objects redefine our understanding of what the universe is capable of. They remind us that for every star that shines peacefully in our sky, there is another out there performing a violent, beautiful, and lonely dance on the edge of the impossible. Now, let us turn our attention to another captivating celestial object, Sirius B, located in the constellation Canis Major. This white dwarf might seem unremarkable at first glance. It is far dimmer and smaller than its brilliant companion, Sirius A, the brightest star in our night sky. But do not let its faintness deceive you. Sirius B holds vital clues to the life and death of stars. The story began in 1844, when German astronomer Friedrich Bessel noticed a slight wobble in the motion of Sirius A, suggesting something was tugging on it. Bessel predicted the existence of an invisible companion, and he was proven right. It was the white dwarf Sirius B. This was one of the first times humanity used gravitational influence to detect a hidden celestial body, a method that has since become a cornerstone of cosmic discovery. A white dwarf is the hot, incredibly dense core left behind after a medium-mass star, like our Sun, exhausts its nuclear fuel and sheds its outer layers. Sirius B is a prime example. It was once a much more massive and luminous star, but over eons, it cast off its exterior to become the compact remnant we see today. To understand its density, consider that while Sirius B is roughly the size of Earth, it contains the mass of the Sun. Compressing that much matter into such a small volume creates a density so extreme that a single teaspoon of Sirius B material would weigh several tons on Earth. Its surface gravity is approximately 350,000 times that of Earth. A person weighing 70 kilograms here would weigh a staggering 24 million kilograms there. Interestingly, Sirius B was once the brighter of the two stars before it collapsed. This role reversal serves as a cosmic reminder that the universe is dynamic. Today's brightest stars may one day fade into obscurity. Although it no longer undergoes nuclear fusion, Sirius B remains scorching hot, with surface temperatures exceeding 25,000 degrees Celsius, fueled by the residual heat from its former life. Over billions of years, it will slowly cool and dim, providing astronomers with a perfect nearby sample to study the cooling stages of stellar remnants. Looking ahead, our own Sun will follow this path, eventually leaving behind a white dwarf. While no planets have been found around Sirius B, it is possible any original worlds were swallowed or ejected during its red giant phase. In the distant future, white dwarfs will cool until they become theoretical black dwarfs, cold, dark husks of stars, though the universe is still too young for any to have reached that stage yet. The drama of a star's life is further exemplified by SN 1998 BW, an extraordinary event that was no ordinary supernova. This explosion challenged the Eddington limit, the theoretical ceiling where a star's radiation pressure balances its gravity. SN 1998 BW first caught the world's attention when it was linked to a gamma-ray burst, GRB 980,425, an incredibly rare coincidence. Gamma-ray bursts are among the most energetic events in the cosmos, and seeing one alongside a supernova provided a catalyst for deep study. When a massive star exhausts its fuel and can no longer support its own gravity, its outer layers are violently ejected, but SN 1998 BW released energy far beyond a typical supernova, earning it the classification of a hypernova. Scientists observed high-speed jets, a signature of extreme collapse, likely occurring when the star's core collapses directly into a black hole. This event pushed the boundaries of stellar physics, showing that under extreme conditions, a star can briefly exceed the Eddington limit, providing a rare glimpse into the chaotic physics of a star's final moments. Another geometric wonder is the Red Rectangle Nebula, located about 2,000 light-years away in the constellation Monoceros. While most planetary nebulae are spherical, this one appears strikingly rectangular, though this is largely an optical illusion caused by our viewing angle and its kite-like structure. Identified clearly in 2004, its unique shape is sculpted by the complex interaction of gas, radiation from the central white dwarf, and powerful magnetic fields. Moving from the local to the universal scale, we encounter the mystery of dark energy. In 1912, Vesto Slipher noticed distant galaxies were redshifting away from us, but the true breakthrough came in the late 20th century via the Hubble Space Telescope. Observations of type Ia supernovae revealed they were much dimmer than expected, meaning they were further away, proving that the expansion of the universe is accelerating, not slowing down. This discovery upended our intuition that gravity would eventually pull everything back together. We know dark energy exists not just from supernovae, but from the cosmic microwave background, CMB, the afterglow of the Big Bang and the distribution of galaxy clusters. Dark energy acts as a counter-force to gravity, preventing clusters from forming at predicted rates and stretching the very fabric of space-time. It even influences time. In the time delay effects of distant supernovae, we see that time appears to flow slower in regions where dark energy's influence is strongest. The implications for the future are profound. If this acceleration continues, galaxies will drift so far apart that they become isolated, eventually leading to the heat death of the universe. More extreme theories, like the Big Rip, suggest that if dark energy strengthens over time, it could eventually tear apart galaxies, stars, planets, and even atoms. While it remains one of the greatest puzzles in modern cosmology, dark energy connects all the phenomena we've discussed, from hypervelocity stars to the massive voids between galactic filaments. Thank you for joining me on this journey through the extremes of our cosmos. I hope these wonders fill your dreams and your day. Until next time.